Hi again, this is Michael Hicks with your Business Administration 602. What I'm going to do in this lecture is go over the statistical part of the class, which overlaps the economics part, but I'll just do the statistics lecture here and then the economics lecture in the next section. And this is just really a review of what we've done in the class so far in each one of these areas, so that when you think about what you might want to go back and review in a later class, or if you're trying to understand how prepared you are, you'll see this. And so I've got these concepts put up here. There are a little bit over a half dozen concepts that we went through in the first 8 weeks of the class that involve statistical analysis, and I'm just going to talk through each one of them. I would encourage you in preparation for the exam to, if you're concerned about something, to go back and look what we did specifically in that section. And then particularly as you go forward in your MBA program, a lot of people keep their books. Of course, these are free. These lectures will be on the YouTube channel, into the distant future, and you can use that as a point to go back to look at some of this material. I particularly would recommend that you have the tutorials on how to make graphics and how to present graphic information. That's such a weak point in MBA students in their early part of their career. And so I would like you not to have that problem in the next few classes. So when we began the class in August, if you guys might hear my dog in the background, I'm sorry. I began the class in August just describing data with statistics, and we use what are called moments, which are the mean, the standard deviation, skewness, kurtosis, variance, to describe a set of data. And we normally, in a business environment or a social science setting or in healthcare, will do that. We're talking about a group of people. We'll talk about the average income in a county or the average home price, or we may give a standard deviation or variance or some other way of describing data that includes a point estimate and then a movement around that point. And so that is available in Excel to do these operations quickly, but they're a central part of presenting data before you analyze it or if you're describing it. And that's where the next piece was the supplement, where I gave you these graphic tutorials to make you better presenters of data in a document or a presentation. And again, I can't overemphasize this. The papers that I see from early MBA students, young graduate students, and then oftentimes people in business are very poor in these areas. And I think you would set yourself ahead if you were good at that. In the next lecture series, I introduced distribution theory with a real special focus on the normal distribution. That's the bell curve. And I pointed out that this would be important in your MBA program because most of the important statistical tests that we're going to perform on samples of data involve assumption of normality. And that's not universally true. We'll do logistic analysis, which is a distribution that has a bigger tail when we're talking about, maybe a Likert scale on surveys, or we'll have analysis in operations research that is yes or no, or it's bimodal. If we're looking at a product, does it meet a standard or not meet a standard? That would be a quality control bimodal distribution. But again, the normal distribution, the bimodal distribution, or binomial distribution, they're the same thing, or a logistic regression distribution, which is a flatter average and fatter tails, are very common in business applications. There are other examples, sensor data, where a value, is limited from 0 to 1, but can take any value like a proportion within that area. There are other distributions, and the reason we worry about these is that the sample that you draw matters. The number of observations that you need to draw to make good inference from samples of different size matters, and the statistical tools that we use to apply them are different. And the idea is the same, but they are actually different. And so that is what I introduced when I talked about sampling and the central limit theorem, which is really a treatment of what are the minimal sizes of distribution or of observations you need to draw inference about a bigger population. How many people would you have to have information about before you could infer something about a different group. And then I turn to what I call the signal-to-noise ratio, which is the heart of statistical analysis. And a signal-to-noise ratio allows us to compare something about a sample of something. It could be people and their height, their demographics, their age, their race, their gender. It could be something about the duration of light bulbs before they burn out, right? That's a number of hours. And when we're gathering this information, we have signal, which is our measurement tool. How well do we measure income, or how well do we measure home values would be examples of a signal that we would have. Or we would have a engineering setup that plugged light bulbs into different in a laboratory and tested their duration. That would be a signal. And then we have noise, which is random variation. If the temperature varies within the laboratory, that could cause some light bulbs to burn out early. We might have categorical data on home values, which would give us some noise. And this noise in statistical environments called white noise. It's in engineering that would be bad signal coming through, if it's electrical engineering, through transmission, and that could be caused by all kinds of problems in the atmosphere. In economics, it comes from variations that we can't explain. So if we're trying to, for example, compare income to education, there's going to be a very strong correlation between the two, but there also is going to be a lot of noise, and the noise could be Bill Gates who didn't finish the semester of college but has reasonably good income, all the way down to people with higher incomes who are working at lower paid jobs because of satisfaction. Somebody with a PhD in history, they decided they didn't want to be a professor. They wanted to do a 9-to-5 job and write afterwards. And these are noise to a relationship. And so the noise can come from measurement error. It can come from unexplained variation. It can come from error in transcribing, all kinds of different things. And we're looking for a high signal-to-noise ratio as evidence that whatever we're testing in our hypothesis is stronger. And so that noise to signal-to-noise ratio it describes statistical tests when we compare means, when we compare variances, or when we compare the reliability of a combined sets of data. So these could be that you hear them as t-tests comparing means, for example, or chi-squares comparing variance, or f-statistics that are joint variance estimates. And they have different names, and these are important. Mostly the names are vary because of applying the same concept to different types of distribution. But the idea is always the same. The signal-to-noise ratio being higher gives us more confidence, less confidence. And all of you have had statistics classes, and you will have more. So don't get bogged down in the chi-squared or the f-test or the t-test or the asymptotic t-test. These are all types of signal-to-noise ratio. I then spent a lecture on business application of hypothesis testing to give you some insight of what you would get in operations research or marketing class. And then I introduced basic linear regression, showed you some examples of various data that actually came from research projects that I'm working on here at the center. And then I introduced the economics model of supply and demand. That supply and demand, I showed you very quickly the algebra, how it worked graphically in the algebra that surrounded creating a reduced form model. I introduced the concern that you can't estimate an individual supplier demand curve because there are outside of observations. All we see in the real world is exchange price and quantity at that price. We don't have all the hypothetical higher price and lower quantity, and lower quantity and higher price available for a supply and demand curve. So we're estimating this using statistical tools, and the reduced form model gives you some insight into the elements of that. And then I work through some examples and the practice problem and the exam practice, and the example that I gave you, the practice exam and then the exam, all involved state or county level data on housing within 3 states. It was Indiana, Texas, and California, as I recall, which were the tools that we used for analysis. And so the statistics component of this course is pretty straightforward in the sense that it is really a tool for covering or complementing the theory that you're going to get in other classes surrounding supply and demand, or why you're doing quality control test, or how you're trying to understand consumer preferences in a survey. Those are classes in economics, in logistics management, and in marketing, or how you would try to select a candidate for a job based on criteria, and that would be a human resource issue. So that's the goal of that statistical work here. This introduction to statistics is not enough to get you through the next classes. You need to pay close attention when you get to the statistical work, but the basic concepts are there. The Substack, or excuse me, the free textbook that I presented to you, I think is adequate as an introductory statistics book. It's not the best that I've seen. It's certainly the best for the price, and I would not be afraid to download that as a PDF and keep it around for the rest of your graduate training. And so with that, we'll stop this lecture and move to our economics lecture.